Dear students, hello. In this video, we will solve two exercises related to the study of numerical function variations. Exercise 1. Study the variations of the function h over the intervals from 2 to positive infinity and from negative infinity to 2. Then, create its variation table over the set of real numbers without including 2. Exercise 2. The functions f and g are defined over the set of real numbers as follows. F is a function that takes a number and associates it with the square of the number, reduced by 3 times the same number, then further reduced by 4. G is a function that takes a number and associates it with 3 times this number, added to 12. Represent graphically the curves corresponding to the functions f and g. Solve graphically and algebraically the equation indicating that the values of the function f are equal to the values of the function g. 3. Solve graphically and algebraically the inequality indicating that the values of the function f are greater than or equal to the values of the function g. 4. Find the intersection points of the curve corresponding to the function f with the coordinate axes. Solution. Exercise 1. The successive operations of the function h are as follows. The variable x is multiplied by 5. 10 is subtracted from the result obtained. The new expression is then raised to the power of 2, meaning it is multiplied by itself. Finally, the inverse of this last value is taken, meaning 1 is divided by the expression obtained. Now, we will study the function over a given interval. The analysis focuses on values of the variable that are strictly greater than 2. Let a and b be two numbers such that 2 is less than a and a is less than b, with both numbers belonging to this interval. We examine how the function evolves by applying the successive transformations. When x is multiplied by 5, the order of the numbers is preserved. 10 is less than 5 times a, which is less than 5 times b. By subtracting 10, this relationship does not change since the same quantity is removed. 0 is less than 5 times a minus 10, which is less than 5 times b minus 10. Raising this new expression, power of 2 is an increasing operation, meaning 0 is less than the square of the quantity 5 times a minus 10, which is less than the square of the quantity 5 times b minus 10. However, taking the inverse of this quantity reverses the trend. We move from increasing progression to decreasing, meaning 1 divided by the square of the quantity 5 times a minus 10 is greater than 1 divided by the square of the quantity 5 times b minus 10. Since a is less than b, it follows that h of a is greater than h of b, meaning the function h is decreasing over the interval from 2 to positive infinity. Thus, we conclude that the function is decreasing over the studied interval. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Study over the open interval. From negative infinity to 2, we consider two numbers belonging to this interval, a and b, such that a is strictly less than b, and b is less than 2. By multiplying both numbers by 5, their order is preserved. 5 times a is strictly less than 5 times b, and both values are also less than 10. Subtracting 10 from both expressions, we obtain 5 times a minus 10 is strictly less than 5 times b minus 10, which is also less than 0. Since the function that raises a number to the power of 2 is decreasing over the interval from negative infinity to 0, this implies that the square of 5 times a minus 10 is strictly greater than the square of 5 times b minus 10. Therefore, h of a is less than h of b. And since a being less than b implies that h of a is less than h of b, the function h is increasing over the interval from negative infinity to 2. Variation table. The variation table indicates that the function h decreases over the interval from 2 to positive infinity. The function h increases over the interval from negative infinity to 2. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Exercise 2. Canonical form of the function f. The function f of x is equal to the expression x plus b divided by 2 times a raised to the power of 2 minus delta divided by 4 times a squared. In this case, a is equal to 1, b is equal to negative 3, and c is equal to negative 4. Thus, f of x becomes the expression x minus 3 divided by 2 raised to the power of 2 minus the quotient of negative 3 raised to the power of 2. Minus 4 times 1 multiplied by negative 4, the entire quantity divided by 4. This expression simplifies to f of x equal to x minus 3 divided by 2 raised to the power of 2 minus 25 divided by 4. Explanation. The canonical form allows the quadratic function to be expressed in a more readable format, highlighting its turning point. This approach makes it easier to understand how the curve is shifted within the Cartesian plane. So we can plot the graph of f by applying a translation using a vector with coordinates 3 divided by 2 and negative 25 divided by 2. Let h of x be equal to x squared. So we can plot the graph of f by applying a translation on the graph of h using a vector with coordinates 3 divided by 2 and negative 25 divided by 4. Graphical resolution of the equation f of x equals g of x. By observing the graph, we notice that f and g intersect at 2 points with abscisses -2 and 8. Thus, the set of solutions to this equation is s equals -2 and 8. Solving the equation, the square of x minus 3 times x minus 4 equals 3 times x plus 12. By grouping all terms into a single member of the equation, we obtain the square of x minus 6 times x minus 16 equals 0. This is now a quadratic equation of the form a times the square of x plus b times x plus c equals 0, where a is equal to 1, b is equal to -6, c is equal to -16. To solve this, we need to calculate the discriminant, denoted delta, which is defined by delta equals the square of b minus 4 times a times c. By substituting the values of a, b, and c, we obtain delta equals the square of -6 minus 4 times 1 times -16. This simplifies to 36 plus 64, which equals 100. Since the discriminant is equal to the square of 10, and it is strictly greater than 0, the equation has 2 distinct solutions. The solutions are given by the formulas. x1 equals the negative of b plus the square root of delta divided by 2 times a. x2 equals the negative of b minus the square root of delta divided by 2 times a. By substituting the values, we find x1 equals the negative of -6 plus the square root of 100 divided by 2 times 1. This simplifies to 6 plus 10 divided by 2, which equals 16 divided by 2, thus 8. x2 equals the negative of -6 minus the square root of 100 divided by 2 times 1. This simplifies to 6 minus 10 divided by 2, which equals -4 divided by 2, thus -2. Thus, the set of solutions for this quadratic equation consists of the values -2 and 8. Graphical resolution of the inequality f of x equals g of x. The function f of x is strictly greater than the function g of x. Graphically, this means that the curve associated with the function f is located above the curve corresponding to the function g. By observing the graph, we notice that this situation occurs when the variable x belongs to the following intervals: from -infinity to -2, excluding -2. From 8 to +infinity, excluding 8. Thus, the set of x values that satisfy the inequality is from -infinity to -2, union from 8 to positive infinity. Algebraic resolution of the inequality. We now need to solve the following inequality. F of x is g of x. This is equivalent to stating that the given expression for f of x exceeds the given expression for g of x. The square of x minus 3 times x minus 4 is strictly greater than 3 times x plus 12. We rearrange this expression to gather all terms on one side. The square of x minus 6 times x minus 16 is greater than 0. Now, we must find the values of x that satisfy this inequality. To do this, we determine the roots of the obtained expression. The roots are -2 and 8. Analysis of the sign table. A sign table is established to analyze the variation of the obtained polynomial. When x is less than -2, the expression is positive. It has the same sign as a, the coefficient x squared. When x is between -2 and 8, the expression is negative. It is the inverse of the sign of a. When x is greater than 8, the expression is positive. It has the same sign as a, the coefficient of x squared. Thus, the values of x that make the expression strictly positive belong to the intervals from -infinity to -2, union from 8 to positive infinity. Conclusion: whether by the graphical method or algebraic resolution, we find the same solution. The values of x that satisfy the inequality are those in the intervals from -infinity to -2 and from 8 to positive infinity. Intersections of the curve with the axes. Intersections with the x-axis. We are looking for the points where the graph associated with the function f of x intersects the x-axis. These points have a y-coordinate equal to 0. The x values of these points are the solutions of the following equation, f of x equals 0, which is equivalent to solving the equation x squared minus 3 times x minus 4 equals 0. Finding the roots of the equation. We have a quadratic equation in standard form where the coefficient a is 1, the coefficient b is -3, the coefficient c is -4. We calculate the discriminant, which is given by the following formula. The square of b, 4 times a times c. Substitute the values. The square of -3 minus 4 times 1 times -4. This gives 9 plus 16 equals 25. Solving the equation. Since the discriminant is strictly positive, the equation has two distinct solutions. They are given by these formulas: -b plus the square root of the discriminant divided by 2 times a, -b minus the square root of the discriminant divided by 2 times a. By substituting the values, 3 plus 5 divided by 2, which gives 8 divided by 2, so 4. 3 minus 5 divided by 2, which gives -2 divided by 2. So, -1. Conclusion. The x-intercepts of the graph are the points where the y-coordinates are 0, and the x values are the solutions we found. Point C with coordinates -1, 0. Point D with coordinates 4, 0. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Intersection with the y-axis. The point where the curve CF intersects the y-axis has an x value of 0. We calculate f of 0 is found by substituting 0 into the expression. 0 squared minus 3 times 0 minus 4. Since 0 squared is 0 and 3 times 0 is also 0, we're left with negative 4. Thus, f of 0 equals negative 4. Therefore, the intersection point of the graph CF with the y-axis is the point with coordinates 0, negative 4. The key property here is that any intersection with the y-axis must have an x value of 0. To verify this property, we substitute 0 into the expression for f and carry out the same calculations. We once again find that f of 0 equals negative 4, confirming that the y-intercept of the graph CF truly is 0, negative 4. Dear student, thank you for watching the video until the end, and next time I say goodbye to you.